Woohoo! Welcome back. Tonight we're going to be working with matrices again. Yay! And I've invited our friend Neo to come help us because we're going to be working with a bunch of new vocabulary. Yay, vocabulary! So basically, we're going to break down solving systems of linear equations using matrices into two categories of final matrix form. The final matrix form. Woohoo! So, the first thing to note, which I've noted right here, the word echelon comes from the Latin and French words for ladder. Latin had one word, the French took it, made it a little different, and then we ended up with echelon. And echelon basically means a ladder or a bunch of steps. So when we talk about row echelon form and reduced row echelon form, we're really referring to the way that it's going to look. And that is that basically we're going to have ones in the diagonal. Woohoo! So a bunch of ones in the diagonal, and then depending on what else we're doing, how else we're going to solve this, we've got slightly different vocabulary. Okay. So to start with, a matrix is in row echelon form if it satisfies the following conditions. Now, these are very formal, and so you can just remember what it looks like rather than what all of this. The first non-zero number in each row, so as you read from left to right, is 1. That's what we got. So we go reading across 1, read across 1, read across 1. So basically we're going to have zeros. Let's see, I think I'm missing. There we go. We got zeros in our bottom triangle. So we're still in triangular form. We've got a bunch of zeros and then ones. The leading entry in each row is to the right of the leading entry in the row immediately above it. That is what causes this stair step or this ladder form. All rows consisting entirely of zeros are at the bottom of the matrix. This means sometimes you're going to have a row and it just zeroes out. So in other words, the information is a duplicate. It just kind of didn't, that row is not going to help us with the solution. And if that comes up, just move that zero row down to the bottom. That's all. So the general idea is you have zeros in the bottom left corner, woohoo, like we're used to, and ones along a diagonal, woohoo. Now, a matrix is in reduced row echelon form if it is in this form and every number above and below each leading entry is 0. This says, okay, so let me go with just 3 so it'll stay simpler. Not only do we all have the ones along the diagonal and zeros in the bottom left, we also have zeros on the top right. So all we have is that ladder and everything else is 0. The general strategy which we've been using is to create a 1 in the first row and use that to eliminate all the non-zero numbers below it. Then create a 1 in the second row and use that to eliminate all the non-zero numbers below and above, and then make a 1 and then make some zeros. So we're going to make a 1, make some zeros, make a 1, make some zeros. We've got 2 different names for the process because it's slightly different techniques. So reducing a matrix to row echelon form is Gaussian elimination. Reducing a matrix to reduced row echelon form is Gauss-Jordan. So row echelon form. Again, let me do the 3 by 3 because it's easier and quick to write. Oh, and here I was focused so hard on what I was doing that I wasn't thinking. So let me clarify. With row echelon form, we're using Gaussian elimination. There's a bottom triangle of zeros, ones along the diagonal, and then other stuff up here. We don't know what's up here. It doesn't matter. Could be anything. Reduced row echelon form, Gauss-Jordan elimination, top and bottom triangle of zeros. So now this is the one that I started drawing because I got too excited. You know when you get really excited about matrices? I know Neo is right with me. He's very excited about matrices. And instead of letting the matrix bend around the math, I tried to bend the math around the matrix. And you know, that's not going to be the way to do it. Plus, I should probably have a spoon somewhere. That might be helpful. So the difference here, you can see the zeros are just in the bottom. And here we're going to have, let me get that around. This is going to be top and bottom zeros. Now, with row echelon form, which we've been using even before we had matrices, we have to use back substitution. So we're going to use back substitution to solve. And here, what's the benefit? Well, the benefit is if you've got a bunch of ones and then you've got some numbers, I should have left the numbers. There are numbers over here, number, then it's easy to read off each variable's value right over there. So what is the benefit of a matrix in reduced row echelon form? It's a lot more work, but you can read the answer out of the matrix without any substitution. Woohoo! So, sometimes the homework will just ask you for row echelon form. Sometimes the homework will ask you for reduced row echelon form. And it really, it just depends on what it's asking for. If you aren't told one or the other, you can choose. Some people always go for this. Some people stop here and then just use back substitution. So it's really up to you how you want to do that. Okay, so let's go ahead and try an example. We're going to use Gauss-Jordan. Now remember, if someone says Gauss-Jordan, we're in reduced row echelon form land. So let's go ahead and go to reduced row echelon form. Okay, this is probably going to take us a little bit of time. And the usual caveat that everybody has a different style, and so your steps may not match my steps. But regardless of which steps we use, if we both use good math and we don't make any mistakes, we'll end up in exactly the same final form. Okay, so first thing is I'm going to rewrite this as an augmented matrix. 3, 2, -3, 10. 1, -1, -1, -5, and 1, 4, -1, 20. So far, so good? Great. So first thing I'm going to do is I've got a 3 up top, and I need a 1 in that important place. So I look through and I see, can I divide by 3? And the answer is I could divide by 3 if I want a lot of fractions, which I don't want, so that's not what I'm going to do. Instead, I'm going to use row 2 or row 3 and pop it up into the first row. And which one you use is really up to you. Because this one starts with 1 and then goes to 4, I'm going to use it. I don't know ahead of time whether that's the best choice, but that's what I'm going to do. So I'm going to take row 3 and I'm going to swap it with row 1. Okay, so my new matrix looks like 1, 4, -1, 20, 1, -1, -1, -5, and then 3, 2, -3, 10. Okay, first step. Second step, once you've got the 1, yay, we got a 1 in the diagonal. Next up, I have to get rid of this 1. I have to make a 0. So I'm going to go ahead and take row 2 and subtract row 1 and move that into row 2. So row 2, and again, you don't have to write as much in terms of notes, you can do this in your head if you're able to. After a while, when you practice, some of this becomes very, very fast, and you start being able to just do the math really quickly. Ooh, almost caught me. So the opposite of row 1, 1, -1, -4, +1, -20. Add 0, -5, 0, -25. Okay. Ooh, and I know a secret. And you probably know a secret too, because you're probably looking at that going, wait a minute, there's some interesting things happening there, isn't there? I'm very excited. Okay, so what's our new? It's like the universe giving us a little present. So our new matrix has the old first row. This is our new row 2. 0, -5, 0, -25, and 3, 2, -3, 10. I'm very excited. Why am I very excited? Because -5 and -25 are both divisible by -5. So I'm going to take row 2, divide it by -5, and put it back into row 2. So I get 1, 4, -1, 20, 0, 1, 0, 5, and then a mess. Unfortunately, this last row doesn't seem like it's gonna be a bit of pain here. But why am I excited? Well, remember our goal is gonna be 1s on the diagonal and 0s everywhere else, and now I got a free 0 right there. So that's very exciting. That 0 popped up and I was like, yay! Okay. Next up, let's see, what are we gonna do? And again, this is up to you and your style. And in fact, I'm following a very traditional route. You don't have to go top down. You can use chaos and just go all over if you want. This is just the traditional route because it's not necessarily the fastest, but it is the most consistent. So I'm gonna use this one to get rid of this 3. So I've got row 3 minus 3 row 1, and I'm going to put that back in row 3. So row 3 is 3, 2, -3, 10, minus 3 row 1. Let's see, that's -3, -12, 3, and then, -60. I'm not thrilled about that. I'm really not thrilled about that because that's gonna, the numbers are gonna get really big and it's just gonna make it a little, it is what it is, right? So let me double check that I've done everything correctly. -3, -12, 3, -60. That looks good to me. Okay, I've got a 0. I've got a -10. Again, not thrilled. I've got a 0, and I've got a -50, and oh my goodness, you guys can't see. I'll move it up. It's happening again. Now that it's happening again, now I'm getting nervous because this shouldn't have happened. This is kind of hard, but okay, let's go ahead. So let's talk about our new matrix. Can you see why I'm feeling a little bit nervous? This is our new R3. So I've got 1, 4, -1, 20, 0, 1, 0, 5, and then 0, -10, 0, -50. And so I'm going to go ahead and say, okay, let's divide by -10. And then so R3 divided by -10 and put that back in row 3. And unfortunately now that terrible feeling is creeping because I realize I'm getting a duplicate row. Let me move it up so you can see. When I divide by -10, I get 0, 1, 0, 5. Matching rows are never a good idea. They're never good because it means that you don't have distinctly different information. So with lines, remember it meant that you had two lines that were actually just the same line. Now with 3x3 systems, it's a little more complicated, but basically it means you didn't have enough information. So, but if we ignore this and I say, okay, I've got a 1 and a 0 and a 0. Awesome. And then I go over here and I've got a 1 here. So what I want to do is I want to get rid of the 4 above it and the 1 below it. So I'm going to go up to the 4 and get rid of the 4. So I'm going to take row 1 and I'm going to subtract 4 times row 2 and put that back into row 1. Okay. So row 1 is 1, 4, negative 1, 20. And negative 4 row 2 is 0, negative 4, 0, negative 20. And now I'm getting nervous again. This is just a very exciting matrix, isn't it? Because I'm going to get 1, 0, negative 1, 0. I'm getting a lot of zeros where I'm not expecting them. Okay, let's take a look at our new matrix. All we can do is keep working until something obvious happens. So my new matrix is going to be 1, 0, negative 1, 0, 0, 1, 0, 5, 0, 1, 0, 5. Okay, that's my new. And then I'm going to say, okay, now I'm going to take this one and work on that one. I got to get a 0. So 1, 0, 0. Then this one in the middle makes a 0, makes a 0. And then this one, which is not a 1, and I'm not sure what I'm going to do, has to make a bunch of zeros. So let's see what happens. So I'm going to take row 3 and subtract row 2 and put that back in row 3. Okay, so row 3, 0, 1, 0, 5. And the opposite of row 2, 0, negative 1, 0, negative 5. Oh no. 0, 0, 0, 0. All the information has been squeezed out. So my new matrix is 1, 0, 0. 0, 1, because this is the new row 3. 0, negative 1, 0, 0, 0, 5, 0. And the answer is I can't keep going. Because normally my next step, up until here, I'm golden, right? I got my 1 and 2 zeros. I got a 1 and a couple zeros. What's the next step? The next step is that has to be a 1. There's no 1 here. There's no information at all here. And so this is as far as we can go. And when something like this happens, what is the name for this? The name for this is, well, first let me write down, we can't go any further. We can't go any further than this. And this is actually a dependent system. Which is great for Matt Damon. But as you can see, Neo is not impressed. Neo's not sure about this. He may call himself out and come back another time because this is a little too much. So basically what happens is I can retranslate this system, and I'll remind you that this system, oddly enough, we're using R, S, and T, so let's go ahead and use that. So I've got R minus T equals 0, so that's row 1. Row 2 says S, right? 0R plus S. Maybe I should write the whole thing out. Would that be easier? Maybe that would be easier. So let me go back because I don't want to be too confusing. R plus 0S minus T equals 0. And then 0R plus S plus 0T equals 5. And row 3 says 0R plus 0S plus 0T equals 0. This is a true statement, right? And when we get a true statement, we know that it's saying basically that we've got some dependency in this. So we don't know the exact answer. But we can come up with R minus T equals 0, and this one tells us that S equals 5. So our final answer, if R minus T equals 0 and S equals 5, we could say, well, I can see from this that if R minus T equals 0, then R equals T, right? So we're going to set up a way to answer this, which is that we're going to say, let T equals A. I'm going to pick the letter A. Then R also equals A, because R and T are the same, and S equals 5. So our general solution will be A, 5, A. So we've got a family of solutions, and as long as R and T equal each other, and S equals 5, we're golden. So it isn't a situation where we have all the choices in the world. S will have to be 5 for this system to work out, to have a solution. But as long as R and T equal each other, we're good. So that is it. Wow, what a wacky matrix. That is kind of a bonkers one. And to be clear, this is Gauss-Jordan form for this matrix. Let's review. Every time we've got a 1, it's in a diagonal. Every time we have a 1, we've got zeros below and above it. And any row that's all zeros is at the bottom. Now, what do we do with this -1? We can't do anything with it. Normally, if we had a 1 down here, we would have used it to get rid of it. But in this case, we don't, because we don't have a regular system. We've got a dependent system with too many options. So if we add another piece of information, for example, if someone had said, oh, by the way, T should be 6, then we would be able to solve it and get the whole thing. In fact, if T is 6, then R is also 6, right? So we could have a solution 6, 5, 6, or we could have another solution 1, 5, 1, you know, et cetera, et cetera. So thanks for sticking it out with me. This was a weird and wacky matrix. And in the next video, we'll keep practicing. We'll work on some other matrices. And hopefully they will be a little less wacky, but you know, regardless, Neo will be here to help us out. Maybe I'll bring a spoon next time and it'll all work out better. And so take a break, you know, shake out the old eyeballs, get something to drink and, you know, rest up, stretch, look at something green, and then, you know that I think you're amazing and incredible, and then come on back and we'll math on.